everybody. It's a great pleasure, personally and otherwise, to welcome Professor Annaswamy from MIT, who doesn't need any introduction. But let me go back a little bit, which is 10 years, when I was a fresh grad from my master's at TU Munich. There was a control lab there, which was chaired by Professor Martin Buss. And she was also there as a scholar. What was the scholar?
Hans Fischer Fellow.
It's a Hans Fischer Fellowship. She was there, which is very prestigious at TU Munich. And we all got an email. I was very new there, from Martin. And she said that we have a very, very special professor and friend who is coming. Please take very good care of her. So I'm not sure if I succeeded then, but I'll do my best today. And she has won numerous awards. It's more of a memory test for myself, I think. But I'll see to a few of them. She's a fellow of IEEE, and in fact, she has got a Best Paper Award in the IEEE Control Systems magazine, and many others to follow. She's a leading name in adaptive control. Her book has more than 4,000 citations. She did her master's and PhD at our state, but at Yale University. And after that, she has been at MIT. So, Sir Annaswamy.
Thank you. Okay. Can you hear me?
Yep.
Yeah? All right. Okay. Excellent. Well, thank you, Abhishek, for that very nice introduction. It is sort of like coming home in a way. Yeah, I came after my bachelor's degree directly to Connecticut, and I was here for about 10 years, and then moved east to Massachusetts. So this route of 91, 84, and 90 is sort of very familiar to me. Though this is the first time I took exit 70 and actually got off the highway. So it is indeed like coming home, and thank you very much for inviting me to come here. My area of research is adaptive control. That's basically where I did my PhD, and so that was about 100 years ago. So I still feel, even after all of these years, we only very barely scratched the surface of adaptation, because it's a fundamental concept that sort of is common to not just engineering systems, but biology, which is really where the name comes from. So there's so much more that remains to be done. And I just want to share with you the excitement and the love that I have for this topic with you, and some of the recent highlights of the research, the results that we have obtained in our lab, and maybe end with some videos. So I've been at MIT since '91, and we work on a number of problems all related to complex dynamic systems. So over the years, we've looked at aerospace systems, automotive systems, cyber-physical systems, and energy systems. Obviously, today's topic, I'll focus on this. So the work that just to say a few words about some of the other spaces, we worked quite a bit with Ford and Bosch, where part of it was related to powertrain systems, controlling things like idle speed and air-fuel ratio, and emissions, like particulate emissions and NOx emissions. More recently, we have started to work at urban mobility problems, how to develop alternate solutions for urban mobility that alleviates congestion using optimization and control ideas. And so here, as the name suggests, we are using toll pricing essentially as a controls knob. So if you want to hear more about that topic, in fact, I mentioned to Abhishek, there are 3 different topics that I could talk about. And so this particular topic is not what I'm going to tell you here, but please come to Copenhagen for the conference on control applications. I'll be giving a plenary talk, and it will be on this topic. We've also worked with Bosch on estimating state of charge and state of health using simple, but at the same time, electrochemically accurate models for real-time estimation of SOC and SOH. We worked on the space that sort of is at the nexus between control systems and implementation, and that's basically our footprint in the cyber-physical systems space, where the idea is to look at real-time systems and embedded systems and the kind of structures and constraints that might be present when it comes to real-time implementation. And say, for instance, if you have a complex network structure, then there might be lots of gateways and communication protocols which might introduce latencies. And if there is a way in which you can interface your control design and co-design the control and the platform, then you can make sure that the implementation is indeed schedulable, which are some of the real-time system-specific performance, and also at the same time satisfy the synchronization or whatever the control goals might be. In the smart grid space, if you look at optimization and control problems, there are a plethora of them in the power systems area. But the new twist is basically that you want to make sure that you're able to integrate solar energy and wind energy in power generation, from the time it gets generated to how it gets delivered, so that all of this electricity consumption is green in some sense, and we're not depending upon. We don't really participate in the greenhouse gas emissions. But that introduces a whole sort of new challenges, and that basically is what is, viewed as smart grid. So we are looking at the space where some of the economic dispatch and control-centric goals have to be revisited, and we're developing some methodologies for doing this, not necessarily just optimization and then control, but some sort of a hybrid set of tools that requires to be initiated in order to realize the smart grid vision. Demand response is an interesting concept. That's, again, is something that we are looking at, where if supply has to equal demand, if supply is going to be intermittent, then demand needs to be varying as well. And so can you incentivize consumers like you and me by giving us rebates or incentives, say, if you were to shift the consumption to a period when you have less of a peak load. And all of this also brings in another interesting way in which you can design infrastructures that interdepend on each other. And so if you're going to have something like wind and solar that is intermittent, which is not always reliable but cheap, but to have that complemented by a natural gas source which is relatively clean and at the same time is reliable and on demand, if there is a way in which you can have a joint partnership between the two, that again can introduce some resilience into the problem, where unused capacity of one infrastructure is used to increase the resilience of the other one. And so that interdependence is a space that we're looking at. So those are all the other things. So what I'd like to focus on today is this. And so if you want to hear about other topics, there might be other venues, and certainly I'm going to talk about this in Copenhagen. So moving forward. So I'm going to roughly go about talking about adaptive control using these three broad steps. So a bit of history. So we'll start with what exactly was the genesis, if you will, of designing adaptive systems in the context of engineering, the stability framework that was introduced, and how we really think about adaptation in the context of the problems that we've looked at and applied to a few problems in practice. And what really distinguishes what was done before and what was brought into the picture that sort of laid the foundations for adaptive control. And given that we've got the stability framework, what exactly needs to be done in order to take this methodology and transfer it to technology? And some of the things that would be relevant in this, the results that we've achieved in this context. And like I said before, I'll end with some videos. So adaptation really is the key word here. And so the idea is that what we adapt is basically parameters in a controller. So we are talking about control, which means there is a notion of regulation. You track around a desired set point, or you track a desired trajectory, whatever is considered as the right thing to do, the desirable thing to do. So because it might be optimal, it might be fast, it might give you the right kind of performance that you're looking for, it might give you accuracy, all of that says that there is a control problem. So typically in any control solution, what we do is that we employ a model. We need to know what is it that the system is doing, so that the controller is essentially an inverse problem, right? So you then shape the input the way you would like so that the output behaves in a desired manner. So you take the plant and you invert it in a way, and so that whatever you're putting in is what you'll get out. And so since you know what you want to get out, that's what you'll put in once you have the right inverse, right? So which means you need a model of the system. which means you need the model structure. So, however, the notion of adaptation is that there is something that is uncertain. So what is uncertain in this particular problem is that we assume that the parameters are uncertain. So if you're operating around some trim point, around some sort of a set point, then you have a certain dynamics, right? And suppose those dynamics are not known because your operating point can vary, your environment basically moves you to a different point and it's unbeknownst to you. And therefore, the dynamics around that point, whatever, say for instance, the Jacobians or the input matrix or the output matrix are things that are unknown. So if they're unknown, then you need to basically utilize some way of estimating that unknown quantity. And what you do is you do the best you can and put in all of your prior information here. And everything that you gather online, you put it over here. So together you use this in order to not only generate the control input, which is what any controller would do, but in addition, you also generate parameter estimates. Right? So that basically is what an adaptive controller is. So it self-tunes its parameters so that together with the parameter estimate and whatever you design as a control input, you are adapting to that uncertainty and at the same time providing a compensatory control action which gets you to where you want to go. So that basically is what the adaptive controller is doing, right? So this notion, if you think about it, is conceptually very appealing. It's like, hey, I have this, self-governing system, so it's smart and it's figuring things out as it's evolving, and so it may make a mistake, but then it figures out because of what happened as to how to correct itself. So this was something that really captured the imagination of some key individuals who were in the position to, basically design and install a whole program. And so it was actually in the context of flight control that there were a lot of, just in parallel with the golden era of control systems where all of the space stuff was happening and optimization, this was happening in parallel too. And in fact, what we know as the control conference right now, the precursor to that was actually known as a symposium of adaptive processes. And so and part of that were all these different symposia that we're talking about, theory of self-adaptive systems, self-adaptive flight controllers. And in fact, they were talking about when designing these aerospace systems, you've got propulsion, you've got aerodynamics, and guidance, navigation, and control. And by and large, the C in the G and C denoted adaptive control systems. So, and there's if you look at even the books that were written at that time, a lot of them were actually on adaptive systems. Bellman's book talked about deterministic processes, stochastic processes, and adaptive processes. So, they were in that line. And Widrow's famous book is also about the algorithms were all, talking about adaptive filters, and that was very much a self-tuning entity. And the servo mechanisms were all, about that. And interestingly enough, the one rule that was actually designed and was very popular was actually has the name MIT rule, which actually was designed by Whittaker, who, as I understand, was a master's student at that time, and came up with a gradient descent algorithm, which not only was it tested successfully, it was actually became part of the Honeywell's adaptive flight control systems and became part of a very successful X-15 program. And there were about 100 flights that flew with this algorithm in place. Unfortunately, it had a bit of a anticlimactic ending because one of the flights actually met with an accident. And adaptive control was basically, it got some of the flack. And it could be very well that it was the adaptive algorithm that was implemented there that led to the crash, because there was not a lot of theory that went into the selection of how those gains had to be tuned. In fact, the Abhishek talked about the Best Paper Award. That was the one where we basically took that apart and we analyzed it and we played like a what-if scenario. Like what if instead of doing that particular adaptive algorithm that they had in the MH96, if they had something that was theoretically more informed, which we know now, that crash could have been avoided.
So what was the problem there? They used a bigger step set or something? Or?
It was two sets of gains that it toggled between, and neither of those gains basically were appropriate for the specific operating condition. So there was an electrical disturbance, and it basically entered a steep dive, and it went into a region where these gains were not really suitable. So neither of them basically provided compensatory action. It went into a limit cycle, and then there was a huge roll, and then followed by a side slip, and it crashed. And so that design space over which the adaptation was done and the information that they were gathering were basically insufficient. So that was
basically outside of the
outside of the flight line, exactly. So what happened afterwards, and rightly so, that people brought in theory. They brought in cautionary inputs, as the title suggests. So that what you're doing really when you design these control systems is to not only introduce feedback, but there is some sort of integration involved, and it's nonlinear. So essentially you have like a nonlinear integral gain controller, and therefore you're going to have wind-up. Anybody who's worked on PI control knows that wind-up is one of the biggest things that you need to worry about, right? So all of these papers that followed, and Patrick Parks' one, for instance, is a seminal one, which basically said you cannot do gradient rule blindly, and it's something that basically can lead you to instability. And the whole Lyapunov stability framework and a lot of the things that followed, and work of Narendra's, work of Jan Landhaus and Carl Ostrom's and Graham Goodwin and Steve Morse basically provided a framework saying this is basically how one ought to think about, analyze, and synthesize adaptive control systems. And that basically led to the foundation. So let me tell you a little bit about what that is. So here are some more technical details. So we all know about, when it comes to control, you start with a dynamic system. So this is a very familiar set of equations. You've got X as a state, U is a control input, Y is the output, it's a set of all quantities you can measure, but X basically captures the most important relevant information, and that everything is nonlinear. But what you do not know, so the extra twist that you normally perhaps do not see in other control problems, is that you have a parameter which is unknown. And so if you know that, if you happen to have that uncertainty, then you need to have an additional complexity in the controller. So this is the adaptive controller. And what does it do? It starts with something called a tracking error. And I'll tell you more about it in the coming slides. So it sort of gives you a target. Right? It's indicative of the size of the uncertainty that the system has. Then omega is a quantity that I'm referring to that corresponds to all of the information that I can gather in real time. It could correspond to the input that I put in, the output, or any kind of filtering quantities or any other states that I can measure, right? So I use all of that, and then what I introduce is a new state. And the new state that I introduce is a parameter estimate for the controller. This could be anything. For instance, let's say your PID is the favorite control design that works very well. It could simply be those PID gains which are no longer fixed, but they're actually states that are varied deliberately. And that could be, so theta C could be your Kp, Ki, and Kd, for instance. It could be MPC, though there's adaptive MPC is right now still something that's complicated to do, and I'll explain that if there's time later on as to why that is the case. Or it could be, for instance, gains of a state feedback that is designed using a linear quadratic Gaussian optimization criterion. Now, what you do is you use a design and nonlinear function, C2, which is a function of all of these variables, and you design it in such a way that this error goes to zero and everything is bound. That is the adaptive control problem. So what you've done, even in the case when F and G are linear, is that you made the whole problem deliberately nonlinear. Why? Because you want to compensate for the fact that this parameter is unknown by deliberately adapting your control gains, because you don't know what the value should be. It should be 5, but it's not. I don't know whether 5 will work anymore. So you search in the space of 5 by watching what the output error E is, the target error E, and trying to adjust it in a direction that minimizes the error. Right? So all of this means that I need to know what the error E is, which brings in the concept of a reference model. So a reference model is like a teacher. So let's bring back, and I'm going to return to the analogy again in a later slide. You're a child and you're learning to walk, and your parent, presumably, is guiding you to teach you how to walk. right? So the reference model is like your teacher, like your parent. And because you're still learning, you're in the very initial stages where you don't know exactly when to take that next step and when to gain that stability and when to move into the next gate, etc., right? So there are these things that you need to learn, and so you need a target. And that target basically is this guy. How do I pick it? Remember that it's not like I know nothing about it. There is some prior information. And that prior information is whatever you know to be the nominal model. And for that nominal model, you will design a nominal controller. And remember, control is an inverse problem. So you would pick this in such a way that the output basically follows a command signal, right? If you remember your control history, that's basically how control came into its own as a discipline, designing servo mechanisms around the time of World War II. So you want this guy to follow this guy. So you design a controller so that automatically you regulate your design to be always around the command signal, right? So that's what this reference model is. So then what do? You hold on to this reference model in order to design, to come up with this target error. How do you do that? You have your actual plan, and you design your controller with some initial estimates, and the output is away from ym by a certain amount. So the difference between y and ym is your error, E. Right? So what you do is that you design your U and your parameter estimate in such a way that Y basically looks like Y command. And in order to really, because Y command is not a well-defined quantity, what you can really, it's not possible. Say, for instance, it's a step input. There's no way in which the output of a dynamic system be expected to follow a step input, right? Because you can't have sharp corners. So think of ym as basically a smooth step. That's what this reference model does. It introduces the right number of integrations into the system so that ym is what you can guarantee to be tracked if there are no uncertainties. So once you pose this problem, so the next step is to say, okay, I'm going to have this output error E, and I'm going to choose my parameter in such a way that this error E is reduced. So to do that, I'm going to start with, so let's assume that the correct value that I have for the parameter is theta star. So if theta were equal to theta star, this error E would be 0. So theta star is the uncertain parameter, and I don't know what that parameter, so what it should be, therefore I pick some theta, right? That's the actual control value that I pick. So there is an error. So I toss a coin, and that's the parameter that I pick for, let's say, API gains. So I say it's 5. But I don't know what the correct value is. The correct value might have been 2. So theta tilde is 3. So what should I do? I need to decrease 5. But that's only because I told you that the correct answer was 3. But in reality, you wouldn't know it, right? So it's basically, the problem is like this. It is equivalent to your being on a hill, and you want to get to the bottom of the hill. That's the name of the game. The problem is you do not know where the bottom is with respect to where you are, right? What you can measure is an E, but that error E is a very complicated signal, has a very complicated mapping to the parameter error. So this error model basically gives you the relationship between theta tilde and E. If that relationship happens to be this very nice convex function, it's easy to solve the problem, right? You would just use a gradient. Why? Because if you're blindfolded, let's say, and you want to get to the bottom, you know what to do. You take a step to the left and a step to the right, tells you which the direction of the gradient is, and you move in the direction opposite. Unfortunately, the whole world is not full of just convex hills, and that's where the challenge is. But if it is, you know that the gradient descent method will work, right? That's sort of all of the principle behind this back propagation used in all of the neural networks. So what you do in this particular case, you adjust theta tilde until j goes to 0. And this is what was done in the MIT rule. And what was pointed out in the 70s by Patrick Parks and a whole bunch of other people is that, no, this doesn't work. You really need a stability framework. And that is what led to the next step. So again, I'm going to keep things very simple so that if there are undergraduates in the room, they can also follow. So I hope that everybody here has seen a first-order transfer function. So let's assume that this is your reference model. So what you're interested in is following a step or any other signal R with some lag. So that's your y sub m. But what you have is some other transfer function, 1 over s minus ap. You do not know what ap is, right? So I have an error, and it turns out that for this particular problem, what I do is that I introduce a state feedback, and in this case, there's only one signal, right? So it's just theta times xp, and the answer would be simply, let's say I put it in with a positive sign, you subtract ap and add minus am. So it's minus am plus ap is what you need in here, so that the closed loop transfer function will look like this. You don't know what AP is, and therefore you don't know what you need to put in. But the solution is actually very elegant. All you need is to have theta of t to be this integral nonlinearity, and that will automatically make sure that E will go to 0 for any AP. So this is what is great about it. The parametric uncertainty can be infinite. It can be AP can be anywhere between minus infinity to infinity, and this problem will solve it completely, make sure that everything is stable, and the error E will go to 0.
I'm assuming the AMs are negative, or?
No? AM is negative, yes.
Okay.
Of course. Yes, you want to have your reference model to be well behaved. Yes, AM is negative, correct. All right? So, though there is some thinking now as to what happens if your reference models are unstable. Is there a way in which, so if you have, so the analogy is that if you have an elderly person and the elderly person is trying to figure out how to get assistance in walking, can another elderly person assist? So you could argue that that reference model there might have some, not necessarily, well, whether or not you want to actually make AM positive, I don't know, but you could have some degree of design that goes into it so that it might be easier for an elderly person to be provided assistance than someone who's young and sprightly. So there's some amount of, philosophical debate one can have about that. Okay, so you can take this notion and make it, any order and any level of complexity. And so this says if I have an nth dimension, then I can still play the same game. I have an error E, and this is basically how my nonlinear integral controller works. This is my reference model. And here is the interesting error modeling. Remember I talked to you about this nice convex hill? That's no longer present here. It's neither, it's actually not, there isn't even an algebraic nonlinearity. It's a dynamic nonlinearity that's sitting between your parameter error and E. Look at what's happening here. If theta tilde is the value, at present, this is the dynamics that sits between theta tilde and E. And so it's a transfer function, so which means that it's dynamic, right? And so it takes a certain amount of time between the time you introduce a change in the parameter to the time it shows up in the target. So you need to really have a dynamic stability framework, and that comes from many other tools, including Lyapunov function. So here's the Lyapunov function that we pick for this problem, where you not only have to worry about the standard equation, quadratic term that you use in order to look at stability of, this is for instance what you do in linear systems, but you have to also introduce these other states which are intentionally introduce additional states, and you have to show that this V is going to be non-increasing, and then you introduce other technicalities to show that E will go to 0. So this says that you can take just the notion of what I talked to you about and use a stability framework to adjust parameters in a problem where the parameters are unknown and still guarantee control-centric goals such as tracking, and of course make sure that it's stable. As you take this forward, we can even take it one step further and bring in the problem where all states are not accessible. So here is where the problem becomes even more challenging, which is that when you have uncertainties, you need to identify and then control, right? So if you think about it, and the identification and control are really duals of one another. You need the entire time in order to identify, in order for all parameters to converge, because it's exponential. But you can't wait till infinite time because you need to control the system now. You've got your flight control problem where there is a certain amount of roll instability, or you've got your, if it's a hypersonic vehicle, your phugoid mode is unstable. So you need to come up with a controller now, not after infinite time, right? So now there is a need to not only do identification but control simultaneously. So these are the problems where adaptive control is really useful, and that's what's happening in here. So here is a very interesting structure where this entity here serves the dual purpose of both an observer and a controller. So it's a very interesting problem where you have to have the right structure so that even when you're identifying, think about it, right? Let's say your goal is that you want to eat good food. So you want to go to a restaurant. When you do the experiment, like you're in a new town, so you have no idea. Let's say there's no internet, there's no Yelp, there's no Google, things to review, or maybe your Google reviews don't agree with your sense of what's good food. So you make a mistake. When you adapt, making a mistake is inevitable, right? Because you have a bad experiment. What does that mean? Your identification, so theta 1 and theta 2 are the parameters, remember? That's what you're identifying. You don't know what the true value should be. So theta 1 and theta 2 are wrong. They could be wrong. This is part and parcel of any adaptive control design. But when it is wrong, the closed loop system is not going to be stable. Everything begins to run away, right? You have to quickly bring back. And that's what this adaptive law is all about. It's a nonlinear integral controller so that when this is off, yp is off, therefore E is large, and therefore that E being large swiftly brings theta to the correct value, or a safe value, if not correct. So this gives you guarantees that everything will be stable in closed loop. I had a discussion with Dugiralo earlier about learning. Now, what is learning? It's something hot topic these days, right, with machine learning. So in this case, learning is the correct value, learning the correct value of the parameter theta 1 and theta 2. Now, that is a different ballgame from having theta 1 and theta 2 go to a safe value where the closed-loop system is stable. Because there are plenty of multiple values of theta 1, theta 2 that will guarantee stability, but only one unique value, which is the correct value of the controller. And then also indirectly, it also means that you learn the plant parameter. So that happens only if the reference input probes all of the eigenvector directions of the problem, and that is known as persistent excitation. So it's a slightly different thing. Okay, I'm sorry, I'm giving a lecture, like a seminar, class, rather than telling you about new results. So now I get to the new results. So it turns out that when you do all of this adaptation, because you have not learned the correct parameter, there are some robustness issues. So it turns out that in order to make sure that even when you adapt, and when you have all of disturbances like parameter variations or model dynamics or disturbances, you have to have certain amount of changes in the way in which you design the adaptive law, or you use persistent excitation. And this was what was done like in the 90s, and that gave us global solutions when you have external disturbances which are bounded or time-varying parameters. So the question is, why, now that you've got all of these results, which gives you a stability framework, it also gives you a certain amount of robustness, what remains so that, that stops you from applying this in practice? Turns out there are a number of problems. The first one is that if you've got unmodeled dynamics, like for instance, let's say, you always have an actuator that actually implements whatever is a control input that you're putting in, and invariably in the control design, you neglect the actuator dynamics, saying, hey, those, it acts very quickly. So in principle, the signal here is exactly the same as that signal, and I can think of this as a straight wire. It's not true in general. You always have unmodeled dynamics, not just due to that, but simply because your control model is often much more simplified compared to the evaluation model.
What about nonlinearity?
Nonlinearity is, again, you can think of as additional perturbations that basically introduces robustness. Turns out that there are no global answers, and this has been an open problem for the past 30 years. The other interesting thing is that if you do the simulations for adaptive controller, and those of you who have worked with PI controllers can really relate to that, when you crank up the gain in any PI controller, you introduce a lot of oscillations. And that's what happens in an adaptive controller too. This is an additional adaptation gain that you can introduce in the nonlinear integral gain. As you keep increasing this, these oscillations get worse. And this is never something that you can actually, if you have this kind of an oscillation, practically you don't want to implement this kind of a technology, right? You really have to get rid of them. The other is that, is it possible, given that you've got this sort of highfalutin, very advanced control design, if you hit it with a very severe anomaly, or you've got all kinds of magnitude saturation and rate saturation, is it possible that your fancy controller can really successfully work and provide the right corrective action, even when, say, for instance, a bird flies into the engine, and still deliver the, satisfactory performance? So these are some answers, some questions for which we have answers. And that's what I'd like to share with you in the next 15 minutes or so. So the first one is robustness to model dynamics. And I'm very proud of this result, which I'm hoping we're about to submit the paper to the transaction automatic control that the community will receive it with the same enthusiasm that I have. And that is that we have a global answer to the question where, when you have robustness when you have unmodeled dynamics, the adaptive controller will be robust. So this is the plant. These are the unmodeled dynamics that we considered. And so if it's a first order, then you just pick a first order reference model and you have this very simple control law. And it turns out that for this class of problems, you can show that a simple projection algorithm along with my nonlinear integral controller will guarantee a solution that is globally bounded. And again, this is something that sort of tells you that even though a system is nonlinear and time varying, it is possible to have something equivalent to a gain and phase margin for this nonlinear controller.
Essentially, you're representing an nth order system by first order one. Is that what you're doing?
No. It's just a first example.
Okay.
So, and the idea, because I want to convey the idea as to why this works. So, when you use a parameter projection, what that is guaranteeing is that you're putting everything inside this tunnel, inside this box. So, but the next step you have to show in order to show that everything is bounded is that you're not going to run away inside the box. So this is what you pick by design in the controller, but this is what I'm guaranteeing exists through my analysis proof. So that's the idea. If you go now to a higher order dynamics, and again, it doesn't have to be second order, it can be nth order. So here is the model dynamics, and here's the reference model, and the theorem basically says that even when you have, so you could make that n, not necessarily 2, that you follow these steps in order to show that everything will still be bounded. And so the idea is, again, basically that you have now 4 dimensions or 2n dimensions, but what you are able to collapse this whole problem into is 2 scalar variables that are most important, which is epsilon 0 and v0, and there are these additional dimensions where they're all driven completely by this, and we make use of this fact and the connection, interdependence between these scalar variables and the n-dimensional variables to guarantee boundedness. And so again, this is just to give you a sample of what we've been able to achieve. So the second one is transients. Yes?
How do you know the unmodeled dynamics, or do they have any particular structure?
So here, what we are assuming is that whatever it is such that you have prior information about what the maximum value of the parameter is that you're going to put in, for which you have, for which this controller will still be robust with the unmodeled dynamics in there. So you know so let's say that there is a maximum value of theta star. Mm-hmm. And if you put that theta star in and you have this closed loop, mm-hmm. it has a certain amount of robustness margin. And the G eta of S is within that.
Okay.
So that's the class of perturbation that I can handle. So the point, therefore, is that this theta max, the fact that I need to know it, and that implicitly determines the class of unmodeled dynamics that I can tolerate. So that's basically so it's an existence type of result. Okay.
This is based on the Abnov approach.
It's a combination. So, it's an interesting thing. So it's a combination of the Lyapunov approach and a careful set of reformulations of the underlying state space. So one of the key things that we had to do is which one? Sorry. Okay, we had to come up with the right transformation of variables. Okay, because we had to really separate it into some key variables that capture all of the impact of the unmodeled dynamics. The second thing we had to do is to break it up, and it turns out that there are some interesting relationships between these quantities that I can measure and the remaining quantities that I'm not able to. And it turns out that there is an absolute stability, where you have a strictly positive real transfer function in the forward loop and a first and third quadrant odd monotonic nonlinearity in the feedback loop that you can cast the whole thing into, and that's what gives you global boundedness. So it's a combination of the Lyapunov stability and the right kind of transformations of variables that we had to adopt. Okay? All right, so here's an next one, which I think, even the last one, the math was pretty heavy, so those of you who are not familiar with might have, it might have been more complicated, but this one is very straightforward and very conceptual. It all goes back to the same idea of the child and the parent analogy that I was trying to make. So a reference model is like a teacher, right? So remember I said there's large transients? We came up with a method to fix it. So now we can design adaptive systems which do not show any of those transients. And the idea is the following. We introduce a feedback gain in here. So what is it that this is doing? So let me see if the next slide. Okay. So you're a child and you're trying to learn how to walk, right? So the question, so if I have a system where I'm asking it to adapt, that's basically the starting point. So when you have no idea, when you have uncertainties and you have no idea what the parameter should be, and you're asked to walk, then it is only understandable that your transients are very poor, right? So remember, my reference model said just walk, right? So that's corresponding to the steps, straight line here. But here is the adaptive system. It tries to, so what does it have to do? It has to approach this dashed line. But it tries to do that. It's still adapting, right? Here is a product of a very pristine linear system, whereas this is an output of a nonlinear time-varying system. So it's impossible to expect that this guy will follow this right away, right? So it overcorrects and then it undercorrects, and so that's why there are these oscillations. But think about it. What if your parent did not just say walk, but gave you a helping hand? That helping hand is basically what this is. So there is an error, and so that error is basically absorbed by the reference model. So instead of saying walk like this, the reference model comes halfway and meets you and says, okay, this is basically how you are supposed to walk. And that closed loop reference model seems to do wonders in terms of fixing the transients. And this is, again, something that we are very happy about. And here's all of the math that basically proves that the transients are indeed contained. So here is the plan, and here's the control input, here's the update law. The stability proof basically says, yes, these are the kinds of L2 norms that you're going to have. And then we can analyze what happens to every signal in the loop. We can look at the reference model, and when you have a closed loop reference model component, you can show, remember there was a feedback gain L, and you can derive bounds that basically relate these feedback gains to as an upper bound to xm, which is the output of the reference model that I'm using in order to derive the target. And then I can also derive the L infinity bounds. The previous one was an L2 bound. Then I take all of that and I use that information to get an L2 bound on what my error is. And once I have the error information, then I am able to get a tighter bound on the reference model outputs, which is what this is saying. And if you pick the adaptation gain to be of the same order as that feedback gain that I used in my closed loop reference model, you can show that the reference model no longer exhibits this peaking phenomenon. And I use that in order to derive the bounds on what my adaptation gain is doing. So why do I have when I have very poor transients, basically the L2 energy contained in it becomes very high. And you want to reduce that. And having the bounds that I showed you basically enables, I can prove, remember all of this has the L, and I pick the right scaling between the adaptation gain and the feedback gain. And that basically gives me an opportunity to go from something like this, where I have a lot of transients, to something that is very smooth, and which basically comes from all of the bounds that I was able to derive,
Can I see that?
which comes because of the L.
By wrongly selecting L?
Okay, so introducing an L gives you an additional degree of freedom.
Freedom.
So that basically gives you a way of optimizing the transients.
Okay.
So certainly, yes, there are values for which you can make it worse, but it gives you also, what we can give is design guidelines, like for instance, this kind of a thing, which helps me have the right balance between improving the transients and having a control goal.
Like a helicopter mode. It could actually be.
Absolutely. In fact, that's a very good point. So here is a case, let me see. Here is a case where it's like a helicopter parent, where you're essentially, think about it, okay? Learning and synchronization are basically trade-offs. If you're always interested in having very good performance, then it's possible to do that without any learning, right? Which is basically what a helicopter parent, you know the expression, right? Those of you who, so it's basically like you're always hovering, right, over your child. And you never let the child make any mistakes because you don't want your child to be hurt. Then the child doesn't learn, right? And that's what's happening in here. So here is a case where there is L is very small. Here's a case where L is very high. And what was shown in here is the right trade-off between synchronization and synchronization, which is here, and learning. See, because here, this is what you want the reference model to be. And whereas the closed loop meets you all the way, right? And so you don't want that. So that's basically the idea in here. So you can see that everything on this side had no L. And so that's the one that had a lot of transients. So you can see that it's completely gone with this closed loop reference model. Maybe I'll skip this. There's another idea. And the idea here is basically that so everything I talked about is adaptation, smooth adaptation. But that's different from fast adaptation. And it turns out that there are regions, when you go through the learning, that there are some spaces where the learning is very, very, very slow. So there, it's slow adaptation. And it's good to know in a nonlinear space, in a state space, given that it's a nonlinear problem, as to where your convergence speed is very, very slow, because then you would design it in a way so that you avoid it. Because that's where you're least robust to disturbances and so on, and that's basically what we have done in here. Okay, so let me take 5 minutes to explain this, and then I'll end with some videos that we have. So the idea here is basically whether or not you can use the expertise of a human pilot and an adaptive autopilot in order to withstand severe anomalies. So when you have an anomaly present, human pilots appear to have the ability to have a better model of what the vehicle response should be and what the performance should be in different scenarios. So what that means is that if, say, for instance, one of your rudder is sticking and is not moving, then there is an anomalous vehicle behavior, and that in turn results in some sort of changes in the vehicle response. And so in many cases, the pilots actually have the ability to tell you, okay, this is the kind of thing that might be happening. So is it possible to use whatever information we have about the pilots so that the right handoff occurs from human to machine and back to the human, etc., so that you can correct the anomaly in the most efficient manner possible? So that's basically what we're talking about in here. So if the actuators and sensors are corrupted, can we make the decisions through the right combination of these two decision-making entities in order to have the best online response and recovery? So the kinds of problems that we looked at are two kinds of anomalies. One where basically the control surface was compromised so that instead of having a B matrix like this, the B matrix was compromised by, so imagine if each of the control input was, the effectiveness basically was reduced. So that was one kind of anomaly that we looked at. And the other one is where there could be simply an increase, a drop in the bandwidth. So you have a lot more lag. So whatever used to be an instantaneous response now takes a certain extra time in order to respond, and so it basically makes the vehicle dynamics higher order. So we looked at these two examples, and so we basically compared. So here is a pre-anomaly model, and here is a post-anomaly model. And so the reference model basically is something that is built based on what the pilot estimates the damage to be. So the pilot says, okay, I think that I have this amount of compromise in the control surface. And the pilot has a certain expertise. So eta being very, very small says that the pilot is not an expert. Eta close to 1 says the pilot is confident, and you can trust. Basically, the trust increases, and together you make up a lambda f hat, and you basically use that information in coming up with the adaptive controller. And here is where an interesting concept can be used. So as human, this came in collaboration with a social scientist who works on basically cognitive models of humans. And so we all have this inherent capacity for maneuver, which we use as a guideline for figuring out how much we can push ourselves. So when we are really faced with extreme circumstances, how do we figure out how much extra energy can we expend? How many all-nighters can you pull before you fall apart, you know? So the way we do that, apparently inherently, we have a metric that says, after I recover from the anomaly, I still have some energy to spare. That's how much I push myself. So that's the capacity for maneuver. So like we always have this inherent monitoring of our ability, and this is, okay, now my body needs to rest, or now I cannot push myself anymore. So we have that inherent capacity for maneuver. And we use that as a directive for saying, okay, all right, if I'm going to be able to, if I'm fully functioning and I'm able to do this task in 5 hours, now that I'm in a compromised state, I'm going to let that become 15 hours. So that's how much I have gracefully let my command degrade, right? So we use that notion in order to come up with a combined adaptive and human pilot control. So we used a closed loop reference model, and we said, okay, my adaptive controller basically is going to have this particular strategy. And what it's saying is that I'm going to adjust how much I'm allowing my control input to saturate. And I'm going to reduce it by a certain amount based on how much capacity for maneuver I want to have at the end after I have recovered from the anomaly. So this information comes from the pilot. Right? So we're saying, no, you don't let your control input saturate all the way, because if you do that, you would have exhausted all the reserves. So we use this to then, and this is the kind of result that we got, and we compared it with conventional fault-tolerant controller. So here is a case, so we had 2 successive failures. So one rudder saturated, followed by another, I believe, in the aileron. So So even after the 2 successive failures, what you're saying is how the side slip responds. So I used to command it by 3. I decided with my adaptive and the shared control design that I need to degrade the command to something like 1.5, and I was able to still track it accurately. So that's what I did with my bank angle, and that's what I did with my side slip. Compared to that, the conventional fault-tolerant controller actually had to degrade the performance significantly. So you can see that the bank angle as well as the side slip angle is much smaller, and it's got a lot of oscillations, and it ends up actually depleting all the capacity for maneuver compared to what we had with this design. So again, so the idea is that we are trying to basically allocate the tasks and have certain things come from a decision-making authority that have slightly complementary skills, because certain things that the humans can perceive implicitly, and that information then is transmitted to the adaptive controller that is able to quickly figure out how much by how. So for instance, this command degradation is completely determined by the adaptive controller, and we were able to get good performance. So then you have the second example where we had a latency change. Here is where, again, what we said was the pilot basically gives the information saying, hey, wait a minute. So here is basically, for instance, the anomaly, where the anomaly occurs, and the pilot uses the looks at how the vehicle is responding to that anomalous behavior and says, wait a minute, the bandwidth is not correct, so you really need to increase the complexity of the corresponding controller. So the adaptive controller switches to a higher order, and you can see that instead of adjusting only 3 parameters, you're now adjusting 4, and when you do that, you have a much better performance. So this is another instance by which the human and the adaptive autopilot is able to work together. So those are the 3 things that I wanted to convey to you in terms of closing the gap. We have implemented it in a number of applications, actually both aerospace and automotive. One example, so these are all the different types of anomalies that we looked at. So there's an actuator failure, there could be time delays, the control inputs can saturate, there could be flexible effects. So one was a generic hypersonic vehicle where the purpose was basically to make sure, even there were uncertainties. For instance, there was a loss of effectiveness, and we wanted to make sure that there were certain regions where the state variables were not allowed to go into, because that could correspond to stall. And so what we were able to show was that our design, which is basically does a much better job in terms of, which is the output feedback compared to the state feedback, which wanders away and goes outside into the undesirable region. And this is another lateral direction example where, again, the adaptive is able to do much better compared to the baseline, where, again, the compromise occurred because of the uncertainties, and we also had a corrupted sensor, and you can see that the red basically wanders out, whereas the output feedback design stays inside and behaves exactly like what it would have done when the corruption was not present. So I'm going to skip the VFA, and let me end with a few videos of quadrotors. So let me skip this in the interest of time. Okay, so these were much before drones were a thing. So our purpose was to show that adaptation works, which means that if there is an online sudden change in the vehicle dynamics, you need to be able to figure out how to fly. So what we did was we took this and we basically, first of all, you can see that the color of the propeller is different because the material is something which we could actually, that was graphite, so this one we could cut. So we cut it and we stuck it together with duct tape. Okay? And then we had a little blade in here. So we then launched it and the blade would pop up. And so what it did was it cut the duct tape when it was hovering. So it basically reduced the moment arm. So the amount of thrust that came from the rotors changed. And so that introduces a roll. Yeah, which then the quadrotor had to adapt to. So we then designed the algorithm, and what you would see in the left side is a standard LQG design, and this one has the adaptive in it. So the student developed it at MIT and tested it, everything fine. He flew to Seattle. It's the same code that he implemented in their lab. And this is all in Seattle. Right now it's when we cut it, so you can see that there is a roll and it crashed. Whereas the adaptive, I don't know if I have a slow motion thing too. I don't know if you saw a little white piece of it. They can see that it basically is able to adjust on flying. And all we did was basically made one of the games theta, which was a very according to the non-unique controller that I showed you. So now that one vehicle worked, we said, I'm going to have lots of them, right? So what we did was we then flew this, and so the idea was to have them fly around in a circle. And when this guy comes to the kickoff position, he's going to fail. So let's go back and fly in a circle, right? So he scampers back. Fortunately, that's even a stronger collision. He gets stuck into the downwash and otherwise he will get it right on. So, and you can see that the footprint, in terms of, it's the same data just superimposed on a cartoon, so you can see how the trajectory changes. So there are waypoints, and the waypoints basically are moved in a circle. So right about now, it fails. So you can see that that's the amount of excursion from the circular path. So now, if I do the same thing again, then he comes to the approximation, you're going to see a figure. See what he does and also what the other two. Momentarily, the others stop and even try to bend backwards. Because there's basically an adaptation in the waypoint, in the guidance command as well. So stop that, it's not noisy. So you can now compare the two, the non-adaptive and the adaptive, and you will see that again when the blue comes to the 6 o'clock, you will see that small the excursion, which is much smaller. So here we introduced two levels of adaptation. One was to the individual vehicle, so it always sort of had its own E and corrected the parameters to minimize that E. But we also had a collective error, where this distance to the nearest neighbor was also something that had to be minimized. So together, so we really used both of them, and one for correcting the control loop, and the other for the guidance loop. And it was nice that they worked together. I'm going to skip this. These are just basically other videos that we have. We ran out of funding before we got into adaptation, but here is just basically aerial robotics, if you will. So the idea is that we wanted to have two quadrotors manipulate a task. So we wanted to not only maintain stable contact, but actually execute the periodic motion. And so we had to worry about the kinematic, we had to worry about what the contact constraints were, and make sure that the contact remains stable even when you introduce dynamics. So we then wanted to change the surface and have uncertainties there and have it adaptive, but we ran out of time. But it's a nice video, so I thought I would share it with you. So here's another one. Again, this too, we wanted to make it adaptive. And so the idea is that you don't know where the hinge is, and so it uses the real-time information in order to figure out the direction of motion. So then it figures out, through small changes and force and position relationship, and opens the door and walks out. So those are all the different things that we've been doing. We're now looking at cyber-physical security. So not only do you have these kinds of disturbances and uncertainties, but deliberate attacks. Are there ways in which we can design adaptive controllers that stay a step ahead of the attacker and figures out the intentions and all of the different disclosure, detection, and disruption attacks? And how do you determine what the online metrics are that one needs to monitor? Because a stealthy attack is one which looks like the standard figures of merit used, like, for instance, the innovation sequence from a Kalman filter. And if that indeed has a significant piece of information, you know that an attack has occurred. But a stealthy one would be one which is successful in having the estimation error blow up, even with the compound scalar vector, like the innovation sequence, remains small. And we are trying to come up with ways in which we can introduce uncertainties deliberately into the software model, which is probably what the attacker is using, whereas we are able to adapt to it and make the estimation error small, and see how we can continue to change the level of detection of those stealthy metrics and stay one step ahead of the attacker. So that's what we're looking at right now.
What if they get into a reference model?
Well, yeah, okay. Then you need to have a reference model for the reference model and figure out how you can keep ahead of it. It's all, you just need to stay one step ahead. That's it. So that's what we're trying to figure out.
It's never-ending process.
Thank you.
Okay, thank you. Questions?
I had a question, curiosity. The way you modify with the loop the reference model to make it somewhat smoother or more reachable in a way, isn't it just a way of imposing constraints on the output of your the model that you're trying to learn? I mean, that's probably an easier way of doing it this way, or
yes and no. So see, it's a very interesting thing that we're doing with a closed loop reference model. See, it introduces. Let me see. I need to wear my glasses. So the feedback is coming from the error, E. That's my target error. And that target error goes to 0. It is guaranteed, independent of the value of L that I choose, right? Therefore, asymptotically, my closed-loop reference model does become the model that I want to track. So because of that, I'm not trying to really change the output throughout the whole time. So this is why I like my analogy of the parent and the child. Eventually, the parent does let go of the hand, but not while it's adapting, not while it's learning. So that's what's nice about it. So that's what this says in here. Okay, this is a different PDF thing, huh?
Yeah, it seemed to open in the browser.
Yeah, okay, let me open it in a different way. Yeah, okay, open with, right?
The first.
There we go. Okay.
Just click no.
So, okay, so this L is coming from the error E. So eventually E goes to 0. So in which case this red line disappears. So it completely is in sync with the spirit of adaptation. So that's why
otherwise you would have to adapt the theta dot, which is the way you adapt the parameters, but then you don't know how much they reflect on the output. Therefore, this is an easier way of achieving.
Right, exactly. And this is not like, so what it is basically is some amount of correction to what you're learning during learning. Exactly. So that's why it really comes in. It's not just introducing a filter.
So you go back to your first order system. I just want to get intuition for what.
Absolutely.
What it is doing,
Yeah.
Your minus integral x
Yeah.
p times e, right?
Yes. Absolutely. This one. Yeah.
So what exactly is it doing?
So what it's doing is that, look at what this is, right? So this is basically an integral controller.
Right.
So your XP, in the simplest case, when there is no reference model, let's say I'm just doing regulation around 0. This
So
is
XP
just
is
E
like
squared.
your gain and then
It's just integral E squared.
Okay.
Okay? And that is the gain. And I'm multiplying integral E squared with E. Because XP and XM are the same.
Right.
So it's just a nonlinear integral controller. That's what the adaptation is. Which is why it's good, and the bad comes because it's an integral controller. They can have wind up.
Right.
Which is why you have the oscillations.
And you end up.
Which is why you need to worry about robustness, because integral controllers can have parameter drift. Which is why you need the robustness.
So, one way we do anti-wind up is turn off the integral control.
Which is what we do. There are notions, there are things called dead zone modification that we've introduced over the years. Parameter projection do the same thing. It just basically puts a bound on it. And it turns out that that's a very good fix, because while you do have the bounds, that just gives you safety that things don't run away, but inside you're adapting. So you are trying to customize. So another way to think about it is that for every uncertainty, I'm providing you with a customized linear design. Because I don't know a priori how much gain I should have. Right. So it is, you can have, for instance, and we have actually implemented them in a precision machine system. It works very well in adaptive PID. Okay. It's really like an alternative to Ziegler-Nichols, which basically self-tunes its gain. And over the years, Carl Ostrom and a number of us have worked on it, that automatically self-tunes its values for the specific uncertainty that you might have in that particular problem.
Just a quick clarification question. You say Whittaker's MIT rule.
Yes.
Is that Phil Whittaker?
No, it's H.P. Whittaker. So he was in the late 60s or something. He was a student at MIT.
Aerostra?
Sorry?
Aerostra, MIT?
Professor? I don't know whether he was there or at Lids. I don't know, but he was. I believe that was his master's thesis, if I am not mistaken.
I have a couple of questions. So
Sure.
The first is, you didn't tell that we could also do it by system identification of the parameters first, followed
Yes.
by the...
You could.
So that's another way of...
You could.
And the second one is, my supervisor...
But so the only problem with that is that, strictly speaking, it'll take infinite time. So it's all infinite meaning what? Very large.
Yeah.
So it's all a question of in your application, whether you have
Recursive.
the luxury to wait until you finish identification, or you need to do control right away.
And also you have this closed loop identifiability problems too, no? You might
Oh
have
yeah,
to
so
watch
he
the
actually
wrong
had the
thing.
persistency of excitation, right?
You can,
Yeah.
but it'll take time. So it's all a
Yeah.
question of in that time, when you're not doing control,
Yeah.
is it okay? Because if you're in midair and you have all these, so where they, by the way, many of these algorithms that I shared with you have, of course, been with some changes, have been implemented in the Boeing production systems. In fact, they love CRM. In many of the cases, they just do CRM, put gamma equal to L. They call it, the student who worked on it, his name is Travis Gibson. They call it the Gibson game. They just put that and they're very happy and they're able to design the adaptive. So it works very well. So the reason why they need the adaptive design, and in fact, they have found that it has an edge over some of the robust control methods, is because many of the robust control methods need to satisfy the sector condition. And when you have a blended wing body vehicle, there are these pressure shocks that build in, and that basically ripples through the aircraft. And when that happens, the net integral of the pressure, which is really what contributes to lift and drag and such, are not necessarily within that sector condition. So you need to have an adaptive method that basically compensates for those changes, and that has to happen right away when the vehicle is flying. So you don't have the luxury of waiting and identifying everything and then doing the control. So in those problems, you need to have an adaptive method.
Okay.
Sorry for the long answer.
Yeah, no. And the other thing is, like, my supervisors in Europe in control used to tell me that what you guys do now in machine learning, we already did that 20 years back using adaptive control. What are your views on that? Do you think they're the same?
For certain things, yes, but not for other things. So you see, all the problems that I talked about, the solutions are are basically relevant in the context of a control problem. So many of the applications where machine learning is used, we are not trying to make X go to X star, or we're not trying to make Y follow Y command signal. So those are control problems. In machine learning, you want to know, is it cancer or not? Is it 1 or 0? Is it blue or red? And many of these are discrete decisions, right? What is the correlation between this and that? So the questions are different. And in those cases, given that there is intrinsically no physical laws that guide you as to what the underlying correlations are, these black box, data-driven, training-based, neural network-based solutions are important. So the two are tools used for two disparate set of problems. So I think what we need to figure out is what's the right problem statement where both tools are needed. And that's something, I don't have a clear answer to that yet, but it's something that we're trying to figure out.
Okay.
So yes, partly we have done that. For instance, if you have an inverted pendulum and you're saying there are lots of uncertainties, I wouldn't use machine learning for that. I would use adaptive control for that, because there are ways in which you can, given that you've got an underlying model structure, which would be the surrogate for 1 over S, 1 over S minus AP is a surrogate for that, you would build your control design based on that model structure. And we know a lot about, kinematics and the equations of motion, etc. So machine learning is the wrong tool for that. But I think there are others where, the kinds of recommender systems and so on that is being used, or even for deep learning, for trying to figure out how the models of the brain, I think machine learning is a very appropriate tool.
Okay. And when I'm walking, let us say I lose a limb, and then I can still adapt myself and start walking. Do you think the algorithm going on inside me is similar to what you say here?
I need to think about that. I don't have at the top of my head type of answer to that. I have to think about it.
Okay. All right. There's nothing here. Yeah.
Yeah.
Nobody else wants to ask a question. I already asked one.
Go for it.
Yeah.
Okay. All right. The question of uncertainty, I from what I gathered, the crucial part of this approach is to have a good reference model, because otherwise you don't have a good reference model.
Yeah.
Is there a way of posing the problem in a stochastic way, in which you have uncertainties and then you can work with densities and probabilities? I'm just wondering.
You could, yeah. You could, I suppose. you need to have some way of figuring out how to learn. So if you have a stochastic element, how do you figure out whether you're making a mistake or not? You have to look at it, and then you have to have some sort of prior information about the distribution, perhaps. And maybe one could argue there is some implicit reference model type of thinking there when you're imposing that, right? So because then if you violate those statistics, somehow you're saying, hey, I need to learn or I need to correct.
KL divergence type.
Yeah.
Beaver error.
Yeah. I mean, I know that people talk about unsupervised learning, but those again are, I think, usually
supervised.
Yeah.
Be supervised.
Yeah.
Yeah, be supervised, but you still could have some kind of uncertainties and build the distribution when you're not sure about the rest.
So again, a gut reaction.
You go that far.
Yeah, my contention is that I think somewhere implicitly there is a reference model notion when you have supervised learning. Yeah.
So this is basically your reference model is like sort of like the IMC type of thing, right? Adaptive IMC is what you're saying.
Yeah, it is. Yes, it is similar to that. Correct.
Okay, and let's thank the speaker again.